Hey guys, welcome back. Day 7, rates and rate laws. All right, so we're going to dive into the rates and mechanisms of chemical reactions. So the rates and mechanisms of chemical reactions. And so what is a rate? When we talk about a rate, a lot of times it's we say rate. So a lot of time rate, think math class, change in position over the change in time. All right? So I'm going 15 miles in 1 hour, that's 15 miles an hour. Now I don't need to be going 15 whole miles in a whole hour of time to go 15 miles an hour. Right? We can be going 15 miles an hour in a car within 10-15 seconds, no problem. Right? So we want to know it's just how much something is changing with time. So in chemistry, right, we care about the change in, we're going to have brackets, right, change in concentration. It's going to be change in concentration with change in time. And so this would be X is our compound. This is the, right, that represents the molarity of X. Substance or species X. All right. So we're looking at how the concentration changes with time. Okay, and this is a very, very important thing, or a topic to consider, right? Because, let's say we have to take pain medicine, right? We can only have so much pain medicine in our system before our system can no longer handle it, right? We can only process so much, right? And just like anything else, like we need to know these rates and reactions too. Right, how fast a reaction can burn, how can we slow it down, can we speed it up? All that is very important, right, when we're designing reactions. So we know we have, in a reaction, we have reactants, and they go to products. Reactants react, products produce, right? And so for the reactants, our concentration I didn't spell that. Spell concentration, right? Decreases. Right? Reactants react, the concentration is going to go down. And so it's going to be a negative number because it's going to decrease. Like, so if you graph it, it's like something, an object slowing down. It's negative. And products, our concentration increases. Okay? And so we know, all right, we know this empirically, but there's actually ways to measure it, all right? So let's take a reaction as an example. N2O5 as a gas decomposing into NO2 as a gas and O2. All right, so you got this going on. Now, we know the coefficients of this reaction are 2, 4, and 1. So the stoichiometry is 2 to 4 to 1. That's very important, all right, for this reaction. So as the reaction proceeds, so if we could start the reaction, if we could just push a button to start it, right, as the reaction proceeds, all right, the concentration of N2O5 decreases and the concentration, which we're going to use concentration of NO2 and O2 increase. It's kind of like we're making hamburgers and hot dogs on a grill for a big group of people, right? The raw hot dogs and raw hamburgers and the buns and all the other stuff, They're all there as reactants, and then we put them on the grill and we put them together, and then they're products, right? All right, the completed hot dogs. So our buns and our hot dogs are going to decrease, and our finished product of hot dogs in the bun that are cooked are going to increase, right? And that's just the rate of how it can go. And when it's you're going at capacity, right? Right, there's a certain rate that you can produce hot dogs. Okay, all right. Now when it turns to like making grilled cheese sandwiches, let's say, the number of pieces of bread and the number of pieces of cheese might not be the same. Some of you might use 2 pieces of cheese and 2 pieces of bread. I don't know. Some of you might do 2 pieces of bread, 1 piece of cheese. Some of you might do 2 pieces of bread and maybe more than 2 pieces of cheese. I don't know. Okay? Right? But there's a rate of consumed and produced. Now, we can express the rate of the reaction in terms of how fast N2O5 is consumed, or how fast NO2 or O2 are produced. So we can do that. Now, very important to note that these rates are not the same, right? Because just going back to the grilled cheese sandwiches, right? Your bread usage to cheese usage, not the same for a lot of people. Okay, that doesn't mean it's right or wrong. I'm just saying it's not the same. Okay, it happens with my house, my ketchup usage and ranch usage of my family is not the same, and that's okay, right? And my kids like ketchup more than ranch, which I'm kind of happy with, but it's still right. They use them, and so the rate of consumption is not the same, and that's okay. So in this reaction, not everything's being used and produced at the same amount, right? And if you look, you guys probably noticed that, or could guess that NO2 is produced at twice the rate N2O5 is consumed. All right. Okay. And you'll notice that the relationship is determined by the stoichiometry. All right. So now we got this thing called a relative rate. So the rate will be equal to, in this case, negative change in concentration of N2O5 change in time. All right. Okay, that's just the rate of N2O5 with time. You could graph it like Y2 minus Y1 over, right, X2 minus X1. We've done that before. It's negative, right, because the concentration of N2O5 decreases as the reaction proceeds. Right? Also, it's good to know that the reaction rate slows as reaction proceeds. All right? So the reaction will go faster at first and it slows down, kind of like popping popcorn. All right? Once it starts to go, right, that popcorn goes and it slows down. And if you do the microwave popcorn, you can burn it if you leave it in there too long. All right. So the relative rates. So we talk about the relative rates of the reaction. You're going to have a rate of the reaction. So when we talk about relative rates, you got a rate, and this is for the reaction. It will equal, in this case, -1/2. That's the coefficient for the concentration of N2O5 over delta T. And it would equal 1/4, positive 1/4, the change in concentration of NO2, change in time. It also equal 1/1. All right, just 1 change in concentration of O2, change in time. All right, so you got the rate of the reaction. That's the overall reaction, the overall process. So it's kind of like whatever process we're making, I need, right, 2 N2O5s, 4 NO2s, 1 O2. And so they're all related to each other, right? And one of the biggest things I see students when I put this on their faces is that they forget that this, I don't want pink, hold on. This right here, that's just a number. That's just a number, like 5 molarity per second, 15 miles an hour, 25 miles an hour, right? It's just a number, right? Okay, and so it's 1/2 of that number. The rate is just a number. They're just numbers. It's just becoming a lot more complicated in the variables. All right. Okay, so let's look at some of this in terms of graphing. All right. So I have my time on this axis, on X, because that's what it is, and we'll have our concentration of N2O5 here. All right. Okay, so we'll start at time 0. Let's say we start there, and what usually happens, it's going to start decreasing, and it decreases and it slows down with time. Right? And you say, well, it never stops. Well, technically, probably not, right? Okay, just like gasoline. Some of us have run out of gas, right? I remember driving a car where if I was accelerating, I'm at 3/4 of a tank. If I'm braking, or actually if I was accelerating, I was at empty, and if I was braking, I was like at 3/4 of a tank, right? And the gas would go back and forth. It wouldn't stay, where it actually is, right? In fact, I use my odometer for my gas gauge rather than my actual gas gauge. I don't know if you guys ever had that. Every time I'd fill up, I'd hit the trip, reset the trip on it so that I knew if I was driving city, 300 miles, I needed to fill up. I didn't care what the gas gauge said. And highway, 400 miles, I had to stop. It didn't matter what my gas gauge said. I just went and filled up. I knew I was pushing it if I was going any further than that. Okay? And so if I were to run out of gas, that doesn't mean that every molecule of gasoline in the tank was gone, right? Because you could still smell it, right? It's just the overall, we say we're out of gas, but we're not actually technically out of every molecule, right? There's still some molecules there. We just didn't get them all out, right? Okay? And so the rate slows down to almost 0, but it doesn't quite get there. All right, so there's 3 rates with here, right? Obviously, there's an average. So we'll take an average. Orange will be my average. Average rate. Now, average can be any point. I can have a first half average, second half average. I can have the whole thing average. So if I'm going to stay from time 0 to this time t, right? Right? I can have, that would be my average rate from there to there, right? So whatever the average was, okay? All right? A lot of times our cars nowadays, the newer cars, have an average speed, right? Your average speed might be 38 miles an hour, or maybe 22 miles an hour, or whatever it is, depending if you do a lot of time idling or not, okay? And so your average speed, right, or your average rate is the whole thing, okay? Any point in time. Then there's something called an instantaneous rate. And that's the rate at any one point. I'm sorry. That's the rate at any one point. So right here, that point, there is the tangent line. So if you did the derivative in calculus, right, the tangent line, that's the rate at that time. So this is your speedometer, right? So if your car has an average rate of 38 miles an hour and you're going 60 in a 45, you can't tell the officer that, well, my average rate is below 45, officer. Doesn't matter. They care about your instantaneous rate, right? That's your speedometer, what you're going. Okay, so the instantaneous rate varies. It's the tangent line to this graph right here. It's the tangent line to the graph, whatever that is. And then last but not least, there is the initial rate, which is the instantaneous rate at t equals 0, which is right there. So the tangent line at t equals 0. All right, we'll use that instantaneous rate soon. So those are your rates. All right, so there's the average rate, the whole thing, the whole reaction. There's the instantaneous rate at any given time. Right, and then there's the initial rate, which is the initial, once you allow the reactants to react, that's the initial rate. Okay. All right. So that leads us then into the rate law. Okay. Oh, those are the examples coming up. The rate law. This leads us to the rate law. And what do laws do? Right, for science here, they predict behavior. All right, they predict behavior. So the rate law is the relationship between the reactant concentration and the rate of the reaction. All right, so my rate is going to be equal to some rate constant K times the concentration of my reactant. All right, so this is any reactant. And the rate constant right, it varies with temperature. Right, as you know, right? So for example, sugar dissolving. We know sugar dissolves in water. Some of us do dishes at home, right? And if we do dishes and we use hot water, things dissolve off the knife, the spoon, the pan, whatever, much faster than if we use cold water, right? Because the rate constant increases with temperature. Okay, that doesn't mean it won't dissolve with the colder water. It just takes a lot longer. All right, and some of us have developed a very high tolerance for hot water in our hands. Me personally, I cannot do very hot water in my hands, but some of us can really have hot water and just things like sugars and all that, sauces, just disappear from plates and knives and stuff. Right, so the rate constant varies with temperature, and we know that it usually increases as temperature increases. And it's quite a lot, actually. All right, so that now then there's something called the order of the reaction. And the order, I'll highlight it blue here. The order goes right there. It's the power. It's the exponent. I'll put an N there. All right, for the number, the exponent. Okay. So the order of the reaction right, is the exponent of the concentration term. Okay, so if n here, if I rewrite that rate law, rate equals rate constant k times n2O5 to the first, right? There's one there or nothing. Then we say the order with respect to n2O5 is first order, right? It's 1. Okay. Now, some reactions, right? Like if I had another rate law, just make one up here. Rate is equal to K times concentration of NO to the second, and Cl2, just like that. That's my rate law. The order with respect to NO is second, is 2. The order with respect to Cl2 is 1. Overall, it's third order. Okay? So now this reaction order is very important, because if I want to make this rate faster, I can, heat it up. Usually heating it up does. All right? But there's a certain limit to how hot we want to, operate things. Like sometimes temperature, like there are temperature windows in which we can operate, and most of our, humans, we want to operate from maybe slightly below the freezing point, maybe, 10 degrees, negative 10 degrees Celsius, to like 40 degrees Celsius at the most, 45, no more than 50 degrees Celsius, really. Right? So that's usually the temperature range we want things to operate in, right? Okay, because we don't really want to go much more than 50 degrees Celsius. That's kind of hot, right? I mean, just think 30 degrees Celsius is 38 degrees Celsius is about 100 degrees Fahrenheit. So we don't operate, 45 degrees Celsius is pretty warm. We don't really want to be outside in that, in the sun like that. And we don't really want to be much below negative 10 degrees Celsius. Now, there are places on the earth where that does happen, right? But we don't really want that temperature. So most of our devices, our cars, our electronic devices, right, they operate in that temperature window. All right, so we don't really want to play. We could just heat this up to 150 degrees Celsius. Well, that's not always the best option for a reaction. Okay, sometimes what happens here, if I double the NO concentration, 2 squared is 4. I 4 times the rate. So having more NO there, right, really increases the rate exponentially, right, by a factor of, it's squared. Doubling chlorine doubles the rate, right? But doubling NO quadruples the rate, okay? And so that's another way we can actually increase the rate. All right. So then, how do we determine these orders? Okay, right? How do I determine? Is it just the coefficients? The answer is no. It's not the coefficients of the reaction. It's not the coefficients. Now, it could be by coincidence, right? Okay. So here's the thing: the reaction order is determined by experiment. Right? Okay. So when we determine the rate law, we use the method of initial rates. All right. So let's look at an example here. I have, let's say NO plus H2 going to N2 plus H2O. All right, so let's say we got 2NO, 2H2, 1N2, and 2 waters. All right, everything's a gas. Let's say everything's a gas. Gas, 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 gas. All right. So in the reaction with of nitric oxide, common name NO, with hydrogen, three experiments were done. All right, with different initial concentrations. All right. Okay, so the question is, what is the rate law? So what is the rate law, and what is the value of the rate constant K? All right, so we got three experiments, three sets of data. We got experiment 1 in green. Where's my mouse here? There we go. Oh, I lost my mouse. Experiment 1 in green here. And experiment 2 in blue, experiment 3 in purple. So we got the concentrations, right? So what can we control? In this reaction, I can control the initial amount of NO, and I can control the initial amount of H2. I cannot control how fast we make nitrogen gas and how fast we can make water vapor. Can't control that. I can only control my initial concentrations, and that's it. So once I have my initial amounts of NO and H2 and I let them go, now I'm just an observer, right? They're doing their thing. They're reacting how fast they're going to react at that temperature, right? So the temperature has to be consistent for all these. All right, and the rate law, of course, is going to be in the form of rate equals K, concentration of NO to some power here, concentration of H2 to some power. All right. So the best way to do this is compare them in the rate law. All right. So I'm going to take experiment 1 over experiment 2. All right, so, and again, it's in this, so the rate is 2.5 times 10 to negative 5, and the units would be molarity per second. All right, obviously it's molarity here and molarity there, right? So 2.5 times 10 to the negative 5th molarity per second over 5.0 times 10 to the negative 5th molarity per second equals, now the K's. The K is going to be the same for all of them, right? Same temperature. We're assuming the same temperature, so the K is going to be the same for all. So the green K is going to be the same as the blue K. All right, the concentrations here, green, of NO, 5.0 times 10 to the negative 4 molar, and H2, 5.0 times 10 to the negative 4 molar. And we have 5.0 times 10 to the negative 4 molar and 1.0 times 10 to the negative 3 molar. All right, so let's just call it X and Z because my Y's look the same. Sometimes you'll see it M and N, P and Q. It doesn't matter, alpha, beta, I don't care what you use. All right, so I have X here and Z there. All right, so how do we do this? We'll just do this math. Well, the rate then, if we do this rate up front, this gives me 1/2, doesn't it? 1/2 equals K over K is 1. This is 5, right? 1 to the x power times, that happens to be, it looks like 1 over 2, 1/2. 1/2 to the z power. So if we simplify this, I get 1/2 equals 1/2 to the z power. So most of us know that z is 1. But what if I didn't? What if I didn't? All right, so if we remember this, log, right, base b of y, equals x, right? And rearranging that, b, base b to the x equals y. I don't know if you remember that from the logs. It's okay if you don't. That's not, you can always reference that. That's not a big deal. Now, in the calculator, if I have this in the calculator, b to what power is y? Okay. All right, because I have 1/2 to what power is 1/2. All right, so in the calculator, I got the log of y all over the log of b. And that'll give me x. In this case, it's z, right? Z is my x. So I do the log of 1/2 over the log of 1/2, and I get 1. Okay. So some of these you might know, and some of these you might not know, and that's okay. So that's why we can do it in the calculator. So z is 1. So I now know z is 1. So that's wonderful. This is 1. Excellent. So now I'm going to compare experiment 2 and 3, right? Because look what happens. Why am I comparing these experiments? So experiment 1 and 2, NO did not change. H2 did. So any deviation in the rate is due to the difference in concentration. H2 has nothing to do with NO. Experiments 2 and 3, any deviation of the observed rate has to do with NO and not H2, right? Because H2 is not changing. This is the scientific method in action right here, right? So if I want to change something, I make one change and see what happens, right? If I make 10 changes, I don't know what's going on, right? I pick on my wife all the time here because she likes to make cupcakes, and she has yet to make a whipped chocolate icing that she appreciates. All right. And I tease her all the time because she doesn't write things down and she doesn't make one change at a time. I'm like, you're not going to figure it out. Like, she's figured out all the other ones she wants to do. She's got a peanut butter one. She's got buttercream. She's got chocolate buttercream. She's got vanilla ones. She's got all sorts of other, icings that she's mastered, and she loves them, and people love them, and it's great. But she doesn't do the chocolate one, and it's hard to get the chocolate one she wants. And you would think it's chocolate, like everything's chocolate, but it's not as easy to work with apparently. And she doesn't follow the scientific method, right? I don't harass her or nothing like that. I let her do it. But she does make amazing cupcakes. I cannot eat them anymore, which is probably a good thing. But she does make amazing cupcakes. She just does not take the time to write down exactly what she's done and make one change with the frosting, right? And she's got some taste testers at home that would love to eat chocolate frosting, but she doesn't do it. So this is how we do the scientific method. You make one little change and then you go on from there. All right, so I'm going to use experiments 2 and 3 now. So in the same form, right? Remember that it's rate equals K, concentration of NO to X power, we don't know, and H2, we know it's to the first, right? We now know it's to the first. All right, so my rate for experiment 2 was 5.0 times 10 to the negative 5 molarity per second. K is K. Concentration of NO is 5 times 10 to the negative 4th. And 1.0 times 10 to the negative 3rd molar for H. Experiment 3, my observed rate is 2.0 times 10 to the negative 4th molarity per second. K, now it's 1.0 times 10 to the negative 3rd molar for NO, and 1.0 times 10 to the negative 3rd molar for H2. Excellent. Alright, so X power right here, we don't know that one. I didn't change color on me. X, we know this one's 1, and we're good to go. Alright, so math. Right? This becomes, if I do this in my calculator, that's 1 over 4 equals 1 times, that happens to be 1/2 to the X power times 1 to the first power, which goes to 1 over 4 equals 1/2 to the X power. So X, of course, is, if you can do it in your calculator, X equals 2. Now, a trick you could do this is I use experiment 1 over 2 and experiment 2 over 3. If I'd have done experiment 2 over 1, I would have done the blue one on top and the green one on bottom. I'd have had everything inverted. I'd have 2 to the Z power is 2, right? I wouldn't have had 1/2. If I'd have done experiment 3 over experiment 2, I would have had 4 to some equals 2 to the power, right? And that's fine too, right? It doesn't matter which ones you do. Okay? All right, so my rate law becomes rate equals K, concentration of NO squared, H2. Ching, all done with the rate law. Now we want to know what K is. How do I find K? Well, you got to pick an experiment. So I'm going to pick experiment 3. I'm going to use 3. Why am I going to use 3? What's 1 times 10 to the negative 3rd? 1 times 10. Those are easy numbers, right? We like easier numbers. So the rate for experiment 3 is 2.0 times 10 to the negative 4 molarity per second equals K times concentration of NO squared, which is 1.0 times 10 to the negative 3 squared times 1.0 times 10 to the negative 3. Okay, and so K would equal, well, if we do the math, that looks like it's negative 3, negative 6, negative 9. Bring it down, right? Positive 9. So that's 2.0 times 10 to the 5th. Now my units would be what? I have to make molarity per second, right? So this is molarity squared, and that's molarity. So that's molarity cubed. So it's 1 over molarity squared times second. And that's my rate. So that's the method of initial rates, and that's doing it, you know, with the math and everything. Now, I will point out there is a way to do this via inspection. And so it depends on how good you are at mental math and how nice the numbers are. All right, what do I mean by that? Well, let's look. If I look here, what happens? Constant. What happens here, right? That's actually a times 2, right? Times 2. What happens here? Times 2. Right? I have times 2 and times 2. So they're both there and there are doubled, right? So that means H2 If I double H2, I double the rate, so it's to the first power. Okay, that's how that one works. Now if I look at the 2 and 3, I double that, but this goes up by a factor of 4. So 2 to what power is 4 squared? So NO is to the second power. So you can do it by inspection as well. It does get funny because you can have 3/2 in there, 1/2, 2/3. You can have a lot of different powers in there. So depends on how good your math skills are. You can always do it this long way, and it will always work. All right. So that's the method of initial rates to help determine the rate law, which comes from, all right, and then there's the relative rates, and we'll do some examples in the next video.